Hello, in this seminar we're going to be looking at solving absolute value equations. Specifically, we're going to be looking at what is absolute value, solving absolute values, the absolute value function, and data visualization. We're going to be looking at this by looking at the Challenger disaster. On January 28th, 1986, the Challenger took off from the coast of Florida with a crew of 7, including a teacher. And here's the teacher on the right. That was Krista McAuliffe. I don't know if I spelled her name right, but that's what it is. After 72 seconds into the flight, the shuttle broke apart. Nobody survived. What was tragic about this, although it was tragic enough, was since she was a teacher, there were many students watching this live at the same time. The Challenger cost $3.2 billion to build. It had previously gone through 9 flights. It wasn't a new Challenger, and it had spent 62 days in flight. Now, how did it happen? Well, shuttle launches take place in Florida because it's a warm climate. The morning of the launch was extremely cold for Florida. It was 28 degrees in Florida on that day. In fact, it was so cold, ice had formed on Challenger, and you can see right here from the pictures from the launch pad. NASA decided to launch anyway. As it turned out, there was a failure in O-rings. O-rings are the rings that seal joints of the shuttle together. The cold temperatures of the day broke the seal of an O-ring, which leaked fluid, which caused the explosion. Here's a picture of our O-rings. Obviously, these are very large O-rings compared to the O-rings we usually see. But these were 38 feet in circumference and were about a 1/4 inch thick, about 6.4 millimeters. Right here is where it failed. You might have seen O-rings like on your sink or your faucet because they create a seal. That's the whole idea of the O-rings. NASA was not totally incompetent. They're filled with very smart people, engineers and like. So they had known about the O-rings and kept a document of them. Here's the picture. You can see the black smoke coming from here. That caused the explosion of the Challenger that killed the astronaut. Now, just like anything, they don't want to make the mistake again, so they went into a detailed study, and the consensus was they were engaged in one-dimensional thinking. They only thought in one direction. The O-ring damage is a point in the system, used a point system, because they're going to be, it's a rocket, lots of pressure. There's going to be some damage, but they kept track of that damage and they thought it was safe. So what happens, they kept this point system, and a larger index means more damage. Most engineered parts are built at room temperature, so a 70-degree launch would assume there's going to be 0 damage. And let's say under a point system, a value of 27 or higher, they had considered dangerous. So if it was 27 degrees or higher, they wouldn't do it. Now, O-rings may expand and not seal during a hot day. So NASA was more concerned about the hot than the cold days. So using the formula where we're going to do predicted damage equals the temperature minus 70, I want to calculate and graph the predicted O-ring damage shown in this table. Now, we're in high school algebra 1. We're not going to get into their point system, but I've adjusted so it's kind of similar to what they did. So here's going to be our O-ring damage. So if on our first case, when the temperature is 70 degrees, if I put in the temperature is 70. I go minus 70, so 70 minus 70 would be 0. So at 70 degrees, we expect 0 O-ring damage. So I'm going to plot that right here. And then 80. So if I go 80, if the temperature is 80 degrees, if I subtract 70, we expect an index of 10 for damage. So when you're at 80, we're going to be at 10. When we get to 90, I go 90 minus 70. That would be damage of 20. And then if we do 100 degrees, 100 minus 70 would be 30. So up here at 30. So we know someplace around 27, you're going to have danger. So they call it off because it was too hot.